Welcome back. Let's find the double integral over r of the function y sine of xy, where r is the rectangle determined by the interval from 1 to 2 along the x-axis, interval from 0 to pi along the y-axis. Now, by Fubini's theorem, we can either integrate. We can write this double integral as the iterated integral, the integral from 0 to pi, integral from 1 to 2, y sine of xy dx dy, where we are integrating with respect to x first and then with respect to y. But Fubini's theorem also allows us to write this as the iterated integral, x going from 1 to 2, y is going from 0 to pi, y sine xy dy dx. Now, so both of them are valid. However, notice that if I integrate with respect to y first, then x is a constant, but then we have to integrate y sine of y, which, if you recall, we have to apply integration by parts to calculate this inner integral. So rather, notice that if I integrate with respect to x first, then y is a fixed constant, then the antiderivative of y sine of xy with respect to x will simply be negative cosine of xy. So now we evaluate that at 2 and 1, that is, remember x is going from 1 to 2. So replace x by 2 and 1 and subtract, so we get cosine of 2y minus cosine of y. And so now we integrate with respect to y, which is going to give us the antiderivative of cosine y is half sine of 2y, and antiderivative of cosine y is just sine y. Plug in 0 and pi now and subtract, we get 0. So even though we could have integrated with respect to y first, so that would be a little bit harder way of calculating this integral, because we have to apply integration by parts. All right, so let's say now that we want to find the volume of the solid that lies above the rectangle R and below the elliptic paraboloid given by z equal to 16 minus x squared minus 2y squared. And the volume we know is given by the double integral over R of the function 16 minus x squared minus 2y squared. So we simply have to evaluate that. Now, since x is going from 0 to 2, y is going from 0 to 2, so we can say that the double integral over R of this function is equal to the iterated integral, where y is going from 0 to 2, x is going from 0 to 2, 16 minus x squared minus 2y squared dx dy. So notice that by writing dx first here, I am implying that I am integrating with respect to x first, and then with respect to y. So the order of this dx dy matters. It tells you in which order you're integrating. So we integrate with respect to x first. So if we do that, we get 16x minus x cubed over 3 minus 2y squared times x. And then we evaluate that at 2 and 0 and subtract. Obviously, when you plug in 0, you get 0. So plug in 2, you got 32, 8 over 3, and 4y squared. We can simplify that to 88 over 3 minus 4y squared. This is what we need to integrate with respect to y, which is pretty easy to do, and at the end we end up with 44. Okay, so that's the volume of this solid right here. Okay, so let me end this video with this remark that if I am looking at the double integral of this double integral over a rectangle R, where this integrand is kind of separable in the sense the integrand can be written as a product of function of x only and a function of y only. So then we can write this as the integral from a to b of g of x dx times the integral from c to d of h of y dy, where the rectangle R is of course the rectangle given by the interval from a to b and the interval from c to d. So for example, if I have the double integral over R of xy dA, where R is this rectangle here, then we can write that as the product of two single variable integrals here. So integral from 0 to 1 of x dx multiplied by the integral from 1 to 2 of y dy. And the reason we could do that is because the integrand is a product of a function of x only and a function of y only. Okay, so I'm going to stop right here. In the next video, we will be looking at how to find the average value of a function over a rectangle.